Hello, this is Mr. Gilmore with the 11.4 areas of trapezoids, rhombuses, and kites. Now that we actually have a good foundation under our feet, we can actually begin developing the area formulas from other simple figures. For example, we're seeing in our title, we're going to be finding the area of trapezoids today, rhombuses, and kites. Let's first dive into reminding ourselves or reviewing a little bit about the trapezoid before we derive its area formula. So a trapezoid's anatomy, remember, if we recall, as we dissect the trapezoid, by definition has precisely one pair of parallel sides. That pair of sides that are parallel, we like to call the bases of the trapezoid, and then the sides that are non-parallel, we call the legs. Now, go back to chapter 5 and think about the what we proved about parallel on chapter 5, and that is that the distance between parallels is known as the perpendicular between the two. As it turns out, I've already talked about these perpendiculars before, such as when we talked about parallelograms. Perpendiculars, these are just simply known now as the height of our of between our two bases. And so what we find as we dissect a trapezoid with the two bases and the height, that is what we're going to be using to find the area. We're going to put it in terms of the lengths of each of the two bases and the height, or that perpendicular distance between our two bases. In the diagram below, the two bases, since we use the letter B to represent both base, we give them subscripts. So we have B sub 1 and B sub 2 to represent each of the lengths of the two bases, and then again H representing the height. And what we're going to do is, here in a moment, we're going to derive the area formula of the trapezoid in terms of these three lengths. So let's actually then jump into our trapezoid area by deriving this formula for us. So again, we have the exact same diagram of our trapezoid. We have base sub 1, base sub 2, those are our parallel sides, and we have that height, which is the perpendicular between the two bases. Let's prove then the area formula, or let's derive an area formula for the trapezoid. Where we begin is with a simple strategy. Connect a diagonal. Now it could be any of the two diagonals in our trapezoid here. I'm going to connect the diagonal from this vertex to this vertex here. So I form this diagonal here along my trapezoid. What happens then is when I form that diagonal, it cuts my trapezoid up into two smaller areas. This triangle with an area sub 1, and this triangle here, actually let me call this triangle here area sub 2, and I'll call this triangle here an area sub 1. So notice that we have, from the trapezoid, two smaller triangles, and those triangles, we have derived area formulas for those two triangles. And here's why. We see that, right, this base sub 1 is really along the same parallel. So there's a parallel extending through base sub 1. Now remember, the height is equidistant. It's the same measure no matter where we're at from one base to the other, which means if I construct a height here, that distance is going to be the same. Now, why that's important is because I'm able then to calculate what the area of A sub 1 is and the area of A sub 2 in terms of our base sub 1, base sub 2, and the height. So let's take a look at the area of A sub 1. That top triangle there. Look at the base. The base is this length here, B sub 1. Look at its height. It's H. So we actually can calculate then, in terms of base sub 1 and height, what the area formula of that triangle is, A sub 1. It looks like this: 1/2 base sub 1 times the height. Let's then take a look at deriving an area formula for the second triangle that's formed with the area of A sub 2. So A sub 2, we also have the length of its base and its height. Take a look at A sub 2. Length of its base is this B sub 2. Its height is actually the same length, H, which means the area of that triangle A sub 2 is B sub 2 times H, right? They're actually the same height because they're equidistant, right? The parallels are equidistant. Well, if we then analyze what is A sub 1, A sub 2 as a whole together, we have the area of our trapezoid is really the sum of area sub 1 plus the area sub 2. So let's use what we just actually figured out about those areas in terms of base sub 1 and height, and base sub 2 and height. Let's put those into this trapezoid expression here. So take A sub 1 out and replace it with 1/2 base sub 1 times height. Take out the A sub 2 and replace it with its corresponding then equation, which is the area of the triangle, 1/2 base sub 2 times height. And then with a little bit of algebra magic, we see that both expressions have a value of h and the value of 1/2, which means we can factor those out. And what we find ourselves by factoring out a half, by factoring out the h, we're left then with a sum of these two things. We're left with a sum of base sub 1 and base sub 2. And there we have it. This is the derived area formula of our trapezoid, which what this says is the area of a trapezoid is simply 1/2 the height times the sum of the two bases. Let me say that again. The area of our trapezoid is 1/2 the height times the sum of the two bases. And so, if we're given a trapezoid where we have the two bases and the given height, we can actually calculate what the area of this trapezoid is. Now, what we'll do is here in a moment, we're going to do an example of our trapezoid. And I tried to pick some non-standard examples that you'll find on the worksheet, some that are just a bit tougher, and I want to walk you through those so you have at least see an example like those. But you will see some standard problems on the homework assignment where I'm going to give you the bases, I'm going to give you the height, and you're going to then give me back what the area of the trapezoid is. But let's take a look at kind of a non-standard example that you'll actually encounter on your 11.4 homework assignment. So we start off with this example of a trapezoid ABCD, and we're given some information about this trapezoid. Now, we are wanting to find the area of this trapezoid. So recall, to find the area of our trapezoid, we actually need three things. We need to know the height, we need to know the length of the first base, and we need to know the length of the second base. So the area of a trapezoid is simply 1/2 times the height times the sum of the two bases. Well, let's take a look at what we have given. We're given the length of BC as a length of 4, we're given the length of AD as a length of 10, and we're given the length of AB as a length of 5. So if you'll notice, we have actually two pieces of information we need. We have the lengths of the two bases, BC and AD, but we don't have the height. Please don't be mistaken. That length of 5 is not the distance. Remember, we need the perpendicular to between the two parallels. So what we're looking for then is we're looking for this length here. We're looking for that h, right, value. Because once we have that, then we'll have enough information to find the area. So the question we ask ourselves is, how do we find that h value? Well, you'll notice there's something else special about our trapezoid given. It's not just any trapezoid, it's an isosceles trapezoid. So take a look. The length of AB is the same length as of CD, which means that's a length of 5. Well, because of this, if we actually drop our altitude in both of these places here from point B and point C, we actually cut our trapezoid into a special shape for ourselves. Notice that this 4, from these 2 points of intersections down here and here, we form a rectangle. And so because we form that rectangle, that means opposite sides must be equal. So the whole thing is 10, but this section from these 2 points of intersection, I'll call those X and Y, that's going to be a length of 4. Why? Because it's a rectangle, opposite sides are equal. So that base BC is 4, then the opposite side must also be 4. Now, why is that important to us? Because here's what we can also do. Notice that the two triangles ABX and DCY, these two triangles formed on the sides of this rectangle, we can prove them to be congruent, right? They've got equal pair of hypotenuses, they got the right angles, and they all will both have the same length of heights, right? Which means those two triangles are going to in fact congruent, and because they're congruent, that means the length of AX and the length of DY have to be the same length. Well, if the total is 10, and this middle section of XY takes up 4 of that, we're left over with 6 units left over to separate evenly between AX and DY, which means we get a length of AX to be a 3. Same thing, same story for DY is a length of 3. Now, why that is important? It's because take a look at the triangle ABX. It's a right triangle, and you now have two sides of that right triangle. You got the hypotenuse length of 5, you got AX's length of 3. We can use Pythagorean theorem to find the length of 4, or find the length of H, which happens to be a length of 4. It's a Pythagorean triple, 3, 4, 5. So now we have everything we need. Base sub 1 we'll call a length of 4. The base sub 2 we'll call a length of 10. And we have our height now, which is also a length of 4. Let's plug those values into their respective positions. So 1/2 the height we just discovered is a length of 4 times the sum of the two bases. Well, the top base, B sub 1, is 4. The bottom base, B sub 2, is 10. And this is the expression we're going to evaluate to get our answer for our area of this isosceles trapezoid. So I'm going to go ahead and simplify this in steps. 1/2 of 4 is 2. I get then a sum of 4 and 10 to be 14, and then I can multiply those two together, and I get my area of this trapezoid to be an area of 28. Okay, 28 is its area. And you're going to see some examples like this on the homework assignment where you're going to have to dig to find the height or missing base, so don't be afraid to do that. So this is kind of a non-standard example. You are going to find some standard examples where I'm going to give you directly the height and the bases, and you can just plug them into your area formula. Okay, now we're going to move on to taking a look at our areas of rhombuses and kites. So let's just remind you of what a rhombus is. A rhombus is a quadrilateral with 4 equal sides. Okay, 4 equal sides. And a kite, we actually saw this definition of a kite as well, and diving into our chapter 6 from first semester, we found the definition of a kite is also a quadrilateral, but this one in this case has 2 pairs of equal adjacent sides and 2 pairs of non-equal adjacent sides. Essentially saying that we have 2 pairs of equal adjacent sides, and not all 4 sides are going to be equal to each other. But the reason why we're talking about the rhombus and the kite to find their area formula is that the rhombus and the kite actually have an overlapping property. That property is that the diagonals of each are actually perpendicular to each other. So this is the common property we find between both the kite and the rhombus, that the rhombus's diagonals are perpendicular and the kite's diagonals are perpendicular. Now, why is this important to us? Because remember, what we're going to do here in just a moment is we will derive the area formula for each the rhombus and the kite. However, because our diagonals are perpendicular in both cases, a rhombus and a kite, we can kill 2 birds with 1 stone, essentially meaning we can prove the area formula for both the rhombus and the kite at the same time because of this property of our diagonals being perpendicular to each other. So what I'm going to introduce to you is what we call the perpendicular diagonals lemma. This lemma is going to lead us into then the derivation for both of our areas of the rhombus and of the kite. And the reason why is because both of these will satisfy this perpendicular diagonals lemma. What this lemma says is this, that if a quadrilateral has perpendicular diagonals, its area then is half the product of its diagonals. Now, why is that? Let's take a look at the derivation. So let's box up our given quadrilateral that has already given to us perpendicular diagonals. And we're going to find that the area of this quadrilateral with perpendicular diagonals is, again, half the area of the product of its diagonals. So in our diagram below, we have this quadrilateral ABCD that's given to us with perpendicular diagonals, and we've boxed it up, right? We've got this rectangle now surrounding our given quadrilateral. So why is it then this given quadrilateral is half the product of its diagonals? We'll take a look first at the dimensions of the rectangle. The dimensions of the rectangle has the same length as the dimensions of the distance of one of our diagonals. So this length right here, which we'll call, let's say D sub 1, is the same length as our diagonal AC. And the second dimension of our rectangle, which we will call D sub 2, it has the same dimensions or the length as our second diagonal here, BD. So we know then that by the dimensions, the entire area of that rectangle is just simply the product of those two, D sub 1 times D sub 2. But how do we know then the area of the quadrilateral ABCD is half of that? Well, let's break this up into chunks. In the first chunk, we see that we've got this other little part of our here of our diagram that's been boxed up essentially. Well, the areas, as we turned out, if this is a rectangle, the area of this shaded region and the area of the unshaded region, well, they're equal to each other, right? Those triangles are perfectly congruent, which then means the area that's shaded is half of that whole area that we had boxed up there. Well, let's rinse and repeat that story, where we have this section boxed up, where we have then the shaded area and the unshaded area, and the area that unshaded is half of that whole. And we rinse and repeat that for this boxed up, that there's another shaded area that's half of the whole. And then we have our last boxed up area here, which means this part is also half the whole. So think about that. All 4 of those shaded little triangles there were half of the whole thing we boxed up. And because those are all half of those whole parts, that means the whole diagram, the whole area of the quadrilateral ABCD must then be half of the whole thing. Well, if the dimensions again are D sub 1 times D sub 2, then the area of our ABCD is half of that. So using our perpendicular diagonals lemma, it moves us then into our derivation of the area of a rhombus and of a kite. So the rhombus and kite formula actually use the exact same formula because of their common property of having perpendicular diagonals. So the area formulas for kites and rhombuses is an immediate consequence of this perpendicular diagonals lemma. Why? Well, because those are quadrilaterals with perpendicular diagonals. And because of that, we find our derived area formula for each, which the area of a kite and a rhombus is simply then 1/2 the product of its diagonals, d sub 1 times d sub 2. To finish off our lesson today, let's take a look at an example. Now, once again, I wanted to give you kind of a non-standard example of one you're going to find on the homework assignment. I am going to give you some nice standard examples where you'll have the links of the two diagonals. You'll plug them into your area formula. You'll give me a number back. But this is a non-standard one, which means you have to do a little bit of digging in to find out its area. So to know the area of this actual given rhombus, we need to know the lengths of its two diagonals. Okay, first things first. When you're given a rhombus, recall two things. First of all, it is a parallelogram. Okay, rhombuses are parallelograms. Second thing, parallelograms have something special about their diagonals. The diagonals bisect each other, which means we can claim AM and MC equal to each other. We can claim BM and DM equal to each other. That's going to be important for us here in just a moment. We are given some information about this rhombus. We're given the side length of AB is 3, which really means we know all four sides because it's a rhombus, our length of 3, and we're given the length of AM to be a length of 2. Now notice that if we're looking for the length of our diagonals, that length of 2 is going to become important. And knowing that the diagonals of the rhombus are actually bisecting each other, it's also going to be handy because we also know the length of CM. So let's call AC. Let me do this way. AC. We'll call that d sub 1. And we already know what the length of d sub 1 is. Because if we take a look at the length of AC, AM is 2, CM is 2, which means the length of AC is 4. But now we need to actually figure out what the length of BD is. BD is our second diagonal, which we'll call that d sub 2. But that is where our question is. What is the length of that one? We don't have that. But we have enough actually to find the length of that. And here's how. Remember one last property of a rhombus, and that is the diagonals are perpendicular to each other, which means this triangle here, ABM, is a right triangle. And if I gave you side AB and the segment length of AM, you have two sides of that right triangle, which means you can find the missing third. So we use Pythagorean theorem. So Pythagorean theorem says, hey, a squared plus b squared equals c squared. Let's call this side length here a. So I have a squared plus 2 squared is equal to 3 squared. I'm going to go ahead and save us some time to solve for a. We get the a value to be the square root of 5, which means I come up here, move my a away. I now know the length of BM. And because I know that, then I also immediately know the length of DM is also 5. Because, remember, the diagonals bisect each other. That's the properties of the rhombus. So now we can find out what is our length of BD, which is our second diagonal, by simply taking our root 5, adding it to the other length of root 5, and we get the length of our second diagonal to be 2 root 5. Now we have d sub 1, check. Now we have d sub 2, check. We can actually find the area. So let's find the area of our rhombus here. Area, remember, is 1/2 d sub 1 times d sub 2. Let's plug in what we know. 1/2 times 4 times 2 root 5. We then multiply that out. My outside numbers can multiply outside numbers. My inside numbers will stay the same. I should say inside numbers with the radicals stay the same. So I have 1/2 of 4 is 2. 2 times 2 is 4. And then we end up with our final answer. The area of this rhombus is 4 root 5. So again, a non-standard example where you do have to do some digging to find the missing length of diagonals. And you can do the exact same thing with a kite, right? Because kites also form those right angles, which means you can use Pythagorean theorem if you're given the similar information. So we've come to the end here of our 11.4 lesson on the areas of the trapezoid, the kite, and the rhombus. If you do have any questions on that homework assignment 11.4, please don't hesitate to email me. With that, be good and do good.